How's it going, everybody? I, of course, am the William Wright, and welcome back to another episode of Quantum Physics Explained at an Elementary Level on Channel Bruce of BDHS TV. So today, I'm going to be talking about Ernest Rutherford's gold foil experiment. So, right now, you're probably thinking to yourself, who was Ernest Rutherford? Well, Ernest Rutherford was a scientist born in New Zealand who did a lot of his work in Canada and England. This would be this man over here. This man on this side is one of his colleagues whom he did the gold foil experiment with. So, Ernest Rutherford set up this experiment in an effort to test the atomic model. What the heck does that mean, you may be asking? Let's take a look. So, a scientist named J.J. Thomson had come up with the plum pudding model previous to Rutherford's studies, and that was assumed to have been correct at the time. J.J. Thomson knew that atoms were neutral overall, but they had negative and positive charges, so he assumed that perhaps it was an overall positive pool, but there were negative charges scattered throughout it. So, the plum pudding model was based off of a popular English dessert known as plum pudding. For those of you who have perhaps never heard of that, it's also kind of like a chocolate chip cookie, in the sense that the cookie dough itself is the positive field, and then each individual chocolate chip is a negative charge. So, how did Rutherford intend to test this atom? Well, the idea is that if I fire alpha particles at a very thin sheet of gold foil, 0.004 millimeters thick, which is, keep in mind, 10 times thinner than one of these pieces of paper that I've got right here. And what will happen to the alpha particles? That was how he was planning on testing it. So, this is the setup he had. He would have a source of alpha particles. He would fire it through a slit in a detection shield, so just basically a pinhole, and then the stream of alpha particles would fly and hit a sheet of gold foil. He wanted to know how they were going to react. So for those of you who have never heard of alpha particles before, they are helium nuclei. Helium, of course, is that gas that you can put in balloons and they'll float around. Or if you're one of those people who likes to inhale helium to give yourself a really high voice, it's that. It's the nuclei of that. Alpha particles are 4 times heavier than hydrogen, which is still not very heavy at all. They are positively charged. They're formed from the radioactive decay of larger elements such as radium. So if you want to think about radioactive decay as like, if you put salt in water, you have salt water. As the water evaporates away, you get whatever was in the water, in this case the salt that's left over, it's left behind, you get that. That's kind of what radioactive decay is. Alpha particles also have a lot of energy, approximately 5.4 mega electron volts of it, acronym being MeV. You probably have no idea what that means. Don't worry, neither did I. So, I did a little bit of calculations. I calculated that to be 2,700,299 volts. For a little sake of reference here, those electrical outlets you have in your home, you know, the things that your parents always told you, don't stick random objects in it because you might get a shock. There's a couple of people in my classroom who like to do that, and they don't listen to their parents, so don't be like them. Those sockets have 110 volts, so a little bit of sake of comparison there. However, alpha particles only have 1.44 times 10 to the negative 15 watts. So that basically means it's a 0, a decimal, 14 more zeros, and then 144. So really not a lot of watts. Standard household incandescent light bulbs are 60 watts, for sake of comparison. Rutherford's hypothesis was that if Thomson's model of the atom is correct, then the alpha particles will travel straight through the sheet of gold foil unimpeded. So, if Thomson's model is correct, he would see a result something like this. In the shield that's set up to detect all the alpha particles, it would only detect on one place, the side directly opposite to where the source is firing them from. The results of this experiment. Did Rutherford see the results according to Thomson's model, or did he see something else? Well, can you imagine what it'd be like if you shot a beam of light at a window, but instead of going straight through the window, it split up and went into a whole bunch of different directions? Or if you fired a laser at a mirror, it split off and reflected out in a whole bunch of directions? That's basically what Rutherford saw. And while yes, most of the alpha particles went straight through the gold foil, some were deflected off path, and a very small number, and approximately 1 in 20,000, bounced straight back towards the source. Odds of that happening are basically 1 in 20,000 is not a lot. You're more likely to toss a coin 14 times and it lands heads every single time. So it's a pretty rare occurrence. This is basically the result that Rutherford saw. And while yes, most of the alpha particles did land here, there were some detected at all parts of the deflector shield. In Rutherford's own words, he described the event as quite the most incredible event that ever happened to me in my life. It was almost as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Oh. Rutherford came up with some conclusions. So, he determined that Thomson's plum pudding model has to be incorrect because it doesn't have anything dense enough to deflect alpha particles. So, atoms must have a tiny, dense, positively charged nucleus, and the electrons must surround the nucleus. When the empty space between the nucleus and the electrons is exactly that, it's empty space. You can't fit anything there. So yes, even in the air that's flowing around us, between every single individual atom of oxygen in the air, the gas that we need to breathe, those oxygen molecules, yes, they're really close together, but you can only get so close together. There is actually empty space there. This is a new diagram of what he envisioned the atom to look like. This is as to scale as I could. The nucleus of an atom is very small compared to the size of the atom. It's 105 times smaller than the radius of the atom itself. So, if this is the nucleus, these would be the electrons orbiting around it. So here's how the results from the experiment differ. If Thomson's plum pudding model was correct, the alpha particles all would have went straight through unimpeded. But because atoms have a nucleus, the alpha particles, if they struck the nucleus, that's how they get deflected. You can almost think of that as if, let's say you wanted to throw a baseball. Now, if you're throwing a baseball through thin air and there's no wind, it'll probably fly straight. But if it's windy, it'll get blown off path. Or if it hits something, it'll be blown off path. That's kind of a rough analogy, but if it helps you, then great. Now, does this particular model of the atom remind you of anything? Something that's really dense at the center and then a bunch of objects orbiting it? Can you say solar system? Now, Rutherford called his new model the planetary model of the solar system because, well, the nucleus of the atom is like the sun, and all of the electrons that are orbiting around the nucleus are orbiting like planets around the sun. Now, approximately 90% of people will tell you that the sun and the earth and all the objects in the night sky are round. I would suggest you listen to those people, because in the atoms, the nucleus is approximately circular, and the atoms overall are approximately spherical as well. Now, one thing that's really important about an experiment is that you have to be able to repeat it, and some more modern scientists did. They came up with some new graphs, so we can actually figure out all of the mathematics for this. These graphs probably do not mean a whole lot to you, and don't worry, they don't mean a whole lot to me either. What they're showing is that the number of alpha particles deflected per angle. And they took a few trials and then basically came up with what's called a curve of best fit. So basically you just plot all the points on the graph, and you'll notice there's just a general trend. They'll start one spot and just go to another. So you basically follow the points along, you just create an arc. They also came up with a mathematical equation. Now, each one of these characters in here represents something, basically trying to solve how many alpha particles are deflected per angle. This is kind of like a very complicated mathematical multiplication table. You know, those things that you'll have the 2 on one side, it'll go 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then down the side it'll always have 2 through 12, and you just follow the numbers across to figure out, like let's say 7 times 6, you go across to 7, down to 6 you'd find 42. That's basically, this is 4, except that you have to just put all the numbers in it yourself, and this is just easier than having a multiplication table, because this has a lot more than 2 variables. Now, Rutherford wasn't able to explain everything that happened in his experiment, and in fact the experiment created some new questions about the atom. Basically, Rutherford did not understand what the electrons orbiting the nucleus actually do, and he was also confused as to why the atoms do not collapse, because opposite charges attract, as I'm sure you know. Like, for example, with magnets, you take a magnet, the north pole, and the other at the south pole, those two ends will stick together. Now, atoms are kind of like that too, in that negative charges attract positive charges, and vice versa. Now, the nucleus of the atom is positive. The electrons are negative. So, why does the nucleus not pull in all of the electrons and just collapse the atom? Rutherford did not know. Another scientist named Niels Bohr would come along to answer those questions. I'm not getting into a great deal about him because I believe one of my colleagues is doing a presentation about him and I wouldn't want to cut in on him. So basically, just to recap, Ernest Rutherford was a scientist who wanted to test the plum pudding model of an atom by firing alpha particles at a sheet of gold foil. Because he saw that the alpha particles were deflected in all different directions, he determined that there must be a small, dense, positive nucleus in every atom, and that the electrons must be orbiting them. I legally have to put a sources cited in this presentation, so all the websites where I got information from are listed here. Now, Modern Language Association, I get that there have to be copyright laws and plagiarism laws, but you really have to make it so complicated? Well, that does it for my presentation. Hope you all enjoyed that and learned something. If you did enjoy this and want to learn more, subscribe to our YouTube channel at Channel Bruce EDHS, and also make sure to follow Mr. Bruce on Instagram at this username right here. Thank you all for watching. Enjoy your day.